For the most part, up to this point, we've been considering only unity feedback systems. So what we're going to consider now is how do we determine the steady state error for non-unity feedback systems. So let's start by considering some general system which I've drawn below. So we see it has some input transducer G1, and so remember a transducer can just help us get our input into a form that's easier to work with in our system. So maybe we're taking a temperature and converting it to a voltage. We also have our controller or our plant G2, and then we have some non-unity feedback H1. And so really I've just written the system this way to sort of give us a little bit of a refresher on our block diagram adjustment or reduction. So let's say we want to simplify this a little bit, so we just have some forward path G and some feedback H. So all we have to do is just move our G1 around that summing junction. So move G1 around our summing junction. And so what we would have to do then is we would multiply the G1 by G2 because of course we moved it to the right. And then we would have to divide our H1 by G1 because of course that G1 was previously not over here. So we have to put in some factor over here so that we're not changing our system relationship. And so again, all of that was just sort of a bit of a review, but we could say then we have some more generic feedback system that looks like this, where again, after we've made that adjustment, our G, our general G is going to be equal to G1 times G2, and our general H is going to be equal to H1 over G1. But going forward, we're just going to focus on G and H. And so what we can see is that because we don't have unity feedback, we no longer have an error signal. So instead of an error signal here, we actually have what's called an actuating signal, and we're going to call this E sub A. So E sub A of S is our actuating signal. And so again, this is not the same thing as our error signal, and that's because we have that H block. And so the reason is because of course our error signal is defined as the difference between our input and our output, but because we have this H block here, we now have some scaled version of our output. So because of that minor difference, we call this our actuating signal as opposed to our error signal. And so what we're going to see in the following videos is we have two options on sort of how we deal with this depending on the system configuration. So the first thing is if we have input and output have the same units, then we can find the steady state error. So let's come down here and say if our input and output have the same units, and so by units I mean volts, amps, newtons, so units. So input and output have the same units, then what we can do is we can find the steady state error. And so of course our steady state error is just going to be our input minus our output, and we'll see how to do that in the next video. But in some cases, our input and output units won't be the same. And so that's because, again, we have this H block here. And so with that H block, of course, if we have some current as an output, maybe our H is multiplying by our resistance, so ohms, so such that our signal coming back here is in volts, and maybe this input signal is a current. Or sorry, maybe that input signal is a voltage as well. Such that we have, of course, we would want to be adding and subtracting volts from volts, but then we would have volts over here and amps over here. So in that situation, what we can do is we can just find the steady state actuating signal. So let's say if we have input and output have different units, then what we need to do is we can find the steady state actuating signal. And so our steady state actuating signal is going to be E sub A as opposed to just E of infinity. So same idea as far as we're letting t goes to infinity. And so we're going to see some more details on that in a couple videos.